Okay, we have ourselves the May 2019 Paper 3, Section A. Here's the actual beginning of the paper, if you don't believe me. But it says that I made a mark, there, fixed it. So it says number one, we have a pretty basic circuit. We have a battery wired in with a circuit element and an ammeter wired in series with the battery, and a voltmeter wired in parallel across the battery terminals. The battery itself is blocked out with what do they call it, maybe a ticked line, a dashed line, and showing the electromotive force and of course the internal resistance of the battery. It says that the current is measured and the voltage is measured, or the potential difference, I should say, the terminal potential difference across the terminals. And it says that the terminal voltage is given as the electromotive force minus the product of the current and the internal resistance. And so we have a data table of current and voltage. Notice that the current is in milliamps and the voltage is in volts. And so it says question continues on the following page. So we have ourselves a nice lovely graph of voltage versus current in milliamps. Also notice something interesting in that the voltage axis, the y-axis, starts at 1.2. It does not start at the origin, so noted. And then A says the student has plotted error bars for the potential difference, which makes sense. Why are there no error bars shown for the current? And the simple answer is that the error bars for the current are too small. But how do we know that? All right, so we can note that, but let's go back and take a look at the current data. Looking at the data table for current, we see that it's mostly in the hundreds of milliamps, but the uncertainty on that is in the first digit. It's plus or minus 1 milliamp. So like even the top number there is almost about 600 milliamps, plus or minus 1. Let's take a look at our graph. So based on the scaling, which I think is appropriate based on the data, we have that 100 milliamps is represented by this very small section here. So 1 milliamp would be teeny tiny. It really doesn't show up on the graph, so the x-axis error bars are in fact negligible. So I would give that maybe 2 points, because saying why that they are too small and why they're too small, it actually uses the verb outline, which, and if you look at the the mark scheme, it says just that delta I is too small to be shown or seen, without actually requiring explanation as to what that means. Well, whatever. They want to give it 1 point, they're going to give it 1 point. Next question. If we're going to be specific, the command term outline. And continues on page 5, because on page 4 we just have ourselves an empty page for funsies. Page 5 is up here. We have sections B and C. In B, it wants the 5, where am I getting 5 from? In B, it wants the EMF of the cell, including the uncertainty, and make sure that you follow significant figures. So let's go back and get the formula and the data. And now, of course, remembering that this is a graph. Duh, we just talked about the graph. So taking a look at the formula, terminal voltage is electromotive force minus IR. Of course, we have the independent variable V is over here, that's on the y-axis, and then we have the dependent variable I, that's a terrible circle, I over here, that's the x-axis. And so I can kind of rewrite this if I really want to get something more along the equation of a line, y equals mx plus b, slope times x plus b. I can rewrite this expression as that the voltage is negative the internal resistance times the current plus the electromotive force. Of course, again, this would be, the voltage would be the y-axis, the current would be the x-axis, negative the resistance, negative the internal resistance would be the slope of the line. I believe that's a negative slope, we'll look at it in a second. And then the electromotive force, of course, would be the y-intercept. So let's look at the graph. Here is our graph, and so in order to get the y-intercept, we don't actually have a line of best fit here, but we can see from the equation that we can expect the graph to be linear, because the formula that they're discussing does follow a line format. So I can draw a line of best fit. Let me get a straight edge. And drew in min and max values as to what the y-intercept could be, based on the minimum and the maximum lines based on the error bars. I can also see that all of the error bars do touch the lines of best fit, so there are no outliers here. These are all legit points. But enough of that, let me actually draw what should be roughly the line of best fit, and there we have it. So looking at that y-intercept, we get 1.6 volts. Our first point is that we figured out that we're supposed to be looking for the y-intercept in order to get the electromotive force. The second point is actually getting the value, which there is some wiggle room. The the mark scheme does say that we'll accept anywhere from 1.59 to 1.61. But of course we need a uncertainty on that, so we look at the uncertainty for the voltage measurements, and it says that all of the voltages are plus or minus 0.02 volts. And here's our answer. But remember, when you're answering questions on an IB test, if you don't put it in their box, they're going to say too bad. So let's go back to the box. And there we have it. And of course, our 3 points, we have our first point by figuring out that we're looking for the y-intercept. We have our second point by actually getting the value of that y-intercept with units. And then we have our third point by identifying the uncertainty with units. Okay, C. Man, did I see C coming, because they wanted the y-intercept, but also by figuring out our equation of a line, we determined that the coefficient on the current is negative the internal resistance. Like we're seeing that right here, negative R. And so in the previous discussion, we already figured out that the slope is negative R, but also note that the graph itself has a negative slope, so that, the slope itself is negative. And then our 2 points here are that figuring out that we're using the slope in order to get the internal resistance, so that's 1 point. And then the fact that if you negate that slope, since the slope is already negative, that does actually give you the value of the internal resistance. That's kind of them to not actually require the solution. All right. Cool. Question number 2. Let's go. We have an experiment conducted to determine how fundamental frequency of a vibrating wire varies with the tension in the wire. I wonder if you could steal that for an IA. That actually sounds like a cool experiment. Anyways, so we have the data shown here. We have frequency versus the fundamental frequency versus the tension. Be careful here. Notice that I almost said frequency versus period. And I'm like, that's not the graph for that. And then I'm like, whoa, that's T, tension in newtons, not T as in period. So don't be a goofball like me. Make sure that you actually read the graph and read the question. So anyway, yes, it is no frequency versus period. And in fact, I can see just by eyeballing that this plot is not linear. And so A says, draw the line of best fit for the data. One thing I like about the regions is that when there's a curve, they say line or curve. But this is definitely not a line. I mean, I guess you can see that. Let me play around with some lines just to kind of prove that. 1 sec. That's the best I can do for a linear fit. That means 2 of the points would be outliers. In a data set of 6, 2 points being outliers, that's a lot. And if, I don't know, like, I see the curve. Hopefully you see it too. Again, to use their terminology, you don't want to create what they call a hairy line. That's a hairy line. You don't want to do that. And so have some faith in your art skills. If you are unsure with your art skills, just take a deep breath and go for it like I'm about to right now. Let's go. Woo! There we go. It's a little wobbly in the middle, but I think that's close enough. The mark scheme says any curve that passes through all of the error bars for 1 point. Let's move on. Question continues on the following page. Here it is. And it's proposed based on the graph that the frequency is given by frequency squared as a constant times the tension. Determine the units for K. So we know the units for frequency. That's normal frequency, not angular frequency. Although, incidentally, I figured this out the other day, the units for frequency and angular frequency are the same. They're 1/seconds. But anyway, tension we know is in newtons, And we need the fundamental SI units, so there better not be any newtons up in there. So let's go. Oops, I hit the wrong button. So this means that the constant is going to be frequency squared over the tension. Frequency we know is 1/seconds. And tension is in newtons, and of course a newton is a kilogram meter per second squared since F equals MA. So now we just have to clean up these units. Seconds to the -1 squared is seconds to the -2, and oh, will you look at that, seconds to the -2 cancels. And so what we are left with is 1/over kilograms times meters, or we could also write that as kilograms to the -1 times meters to the -1, which is what the mark scheme says. And look at that, I got it within the box, so nobody will have a cow. All right, so that's 1 point. Then we have BII. Now, BII is pretty straightforward. It writes out a pair of quantities, and when you plot them out, enable the relationship F squared equals a constant times the tension to be verified. So that relationship says that the square of the frequency is directly proportional to the tension. So if you were trying to verify that, then maybe you should plot the square of the frequency as a function of the tension. Seems like it makes sense. I'm looking at the mark scheme, and they also have some alternatives. If you didn't want to square the frequency, you would also take the square root of the tension, and that would work. There's like another element here that I don't know that you need to recognize in order to answer the question, but I think the intent is there, and it behooves me to illuminate that for you. It gave the relationship that F squared equals KT, and it says it's proposed that that's true. The reason why it's proposed that that's true goes back to the actual original graph. So if we look at the shape of this graph right here, you might recognize this graph as having the form y equals radical x, or in this case, sorry, I was going to say F equals radical t, but that's what would make it linear. That's not what's actually being shown right now. So of the form as it is, plotting the frequency versus the tension yields the graph shape of y equals radical x. Now, if we actually wanted to make this linear and actually directly proportional, we could, of course, square both sides, which would yield y squared equals x. And actually, we don't really know the slope of that. Y squared equals x implies that the slope is 1, so really it's y squared equals some constant times x, which is what actually the question says on the next page. This is where they're getting that the frequency squared equals a constant times the period. And so, yeah, if we squared I'm sorry, I got distracted. If we squared the frequency and plotted frequency squared versus the period, that would get rid of the curve, and it would linearize it. By it, I mean the data. And them, because data is plural. But whatever. And then I started to make additional notes in II, which is only 1 point. But those additional notes are actually addressed in III, where it says, describe the key features of the graph if it is to support this relationship. So looking at the function, F squared equals a constant times the period. That's the equation of a line. Of course, B is the y-intercept, but there is no y-intercept in this expression. That y-intercept would be 0. And so this is what we call, ding, 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 directly proportional. So directly proportional has 2 conditions that must be met. The graph must be linear, and it must also pass through the origin. Based on the plot from the graph, it looks like if you do square the frequency, that data would come out to be linear. Whether it passes through the origin remains to the same. I'm going to use one of the classic, it remains an exercise for the reader to determine that. That's an inside nerdy joke anyway. Oh my gosh, here I am carrying on like a buffoon, and it's actually a 3rd question. All right, let's get down to brass tacks. Just double checking there's not a 4th. Yes, section B is the next page. So let's just knock this out, and I can stop wasting your time. So here we have an interference pattern caused by 2 slits, double slit, and that's the Young's double slit apparatus. And we are given values for the distance from the slits to the screen down in A, and it says the uncertainty on that. It actually says measured using a ruler with a small scale division of 1 millimeter. It says the fringe separation S has an uncertainty of 0.1 millimeters, and then the slit separation has a negligible uncertainty. And it says that the wavelength is calculated with lambda is little s little d over big D. And so lowercase d, little d, is 0.200 millimeters, s is 0.9 millimeters, and the capital D, big D, is 280 millimeters. Find the percentage uncertainty in the wavelength. So we're using a formula not so much to calculate wavelength, but to figure out its percentage uncertainty. Now, all of the relationships here are either multiplication or division, so we're not going to be dealing with absolute uncertainty, but we'll need to figure out percentage uncertainty and proceed from there. For D, I'm going to say there's no uncertainty. Yes, it's negligible, but for the purposes of our calculations, it pretty much comes out to no uncertainty. So wavelength is given as, and it actually says to show some evidence of the use of this calculation in the mark scheme, so I will write it down. That the little s, the fringe separation, times the slit separation divided by the distance from the slits to the screen. And of course, the slit separation has no uncertainty, but the fringe separation does, and the distance to the screen does. So since I'm doing products and quotients, multiplying and dividing, I'm going to be converting to percentage uncertainty, and whether you multiply or divide, you always add percentage uncertainty. And so my wavelength uncertainty is 11.3%. I gotta be honest, I'm not entirely sure how to process the significant figures on the percentage. I see that the mark scheme accepts 11% or 10%. So I did get 11%, but I don't know. I have additional questions for myself. But in any case, it's you do wind up with a percentage uncertainty of 11%, which is what they asked for. And again, to be clear, in terms of the points, there are 2 points here. They were looking for some kind of indication that you understood that you are using products and quotients. They're by the formula, right? So that's 1 point right there, and then the second point is for the answer right there. And then for B, it says, how could you get a more reliable value for lambda? So just as a reminder, we have that the lambda is equal to the fringe separation times the slit separation divided by the distance between the slits and the screen. All right, so if you wanted a more reliable value, I mean, collecting more data is never a bad idea, and that actually is one of the answers they'll accept. And again, to be clear, sometimes collect more data is like, oh yeah, collect more data. And it's like, well, what the heck does that mean? I don't really know. So in this particular instance, the data that's being collected, the distance to the screen remains rather fixed, and then the distance between the slits also remains rather fixed. But in terms of the fringes that you observe based on the wavelength of the light that you're using, you could measure one slit, one fringe distance, you could measure another and another, and you could just measure more fringe distances, because it's not that there's one fringe, there's multiple fringes. So measure as many separations as you can get, and then maybe take the average of those in order to get a value to use for this equation. So maybe measure more fringes and take the average. It's actually one of the things that they mention in the answer key, take the average. That's one thing you can do. Another thing you can do is that the distance from the slits to the screen, the measuring device for measuring that, has an uncertainty of, it measures down, it actually doesn't say what the uncertainty is. What did they say specifically? Yeah, it says measured using a ruler with a smallest scale division of 1 millimeter. Incidentally, little side note, my father was an engineer, and he said that engineers don't refer to rulers as rulers, they refer to them as scales. And I remember when I was in high school, he would constantly correct me. He'd be like, oh, that is a scale and not a ruler. And I'd be like, who cares? No one cares. But if we're talking about HL physics, they should have used the word scale instead of ruler. All right? Okay, I'm writing a letter. Anyway, so I'm sorry, I said I wouldn't waste your time, and I'm wasting your time. But I am reminded that I used for a capital D, I used an uncertainty of plus or minus 0.5 millimeters, and I didn't explain why. It's half the least division, which was given, 1 millimeter, was given in the description of the problem. It says it right there. And so the uncertainty is half the least division, and that's where I'm getting the 0.5 from in A. But if that uncertainty is fixed at 1 millimeter, and I can increase that distance from the slits to the screen, then that 1 millimeter out of a larger capital D value in millimeters means that you're going to decrease that percentage uncertainty, therefore decreasing the overall percentage uncertainty in your value for lambda. So that would be a good thing to do. But that right there, that is two things you can do. So 1 point, 2 points, and I think that satisfies the question. And that ends Time Zone 2, May 2019, Paper 3, Section A. Yeah, I just saw Section B, but that's actually the next page of the mark scheme. And that's it. So I look forward to practicing more of these, but that's it for that solution set. And thank you. Bye.